Okay, welcome to iChem lesson 13 on basic stoichiometry. We are basically going to combine units 4 and 5 here and add one more kind of step to our dimensional analysis, one more ratio. So we're going to always be starting with a balanced chemical equation. You have your reactants, hydrogen gas and oxygen gas. We can sort of add a connector to our mole maps to connect between different elements or different compounds within a balanced chemical equation. When you're in moles, you can freely move between any place in your reaction. And that statement will become a little bit more clear in a minute. But it has to be within moles. So last unit we practiced how to get from particles to moles, mass to moles, and volume to moles. The previous unit we practiced how to get a balanced chemical equation. Now we're going to put that together by introducing this new term called the mole ratio. So I want you to write down what a mole ratio is. Mole ratio is the coefficient in a balanced equation, and that represents the number of moles. Or I guess I should say rather, mole ratio uses the coefficients in a balanced equation that represent the number of moles. We basically have a mole ratio as a statement that compares the number of moles of one compound to the number of moles of another compound in the same reaction equation. And it's very, very crucial that this is a balanced equation because we're essentially looking at the coefficients. We can say a new ratio. There are 2 moles of hydrogen for every 1 mole of oxygen. And this came just directly from the coefficient in front of hydrogen is 2, and the implied coefficient in front of oxygen is 1. This is just another conversion factor that goes in our dimensional analysis. So I'm going to solve a simple problem and then give you some specific steps, and then we'll solve like a slightly more difficult problem. So here's your example. If hydrogen gas and oxygen gas react according to the equation above, then how many moles of oxygen are needed to react completely with 0.64 moles of hydrogen? Okay, so I look up here, my equation is already balanced. I'm underlined already in this equation are what I'm starting with, what I know, my given, 0.6 moles of hydrogen, and what I want. I want to know how many moles of oxygen. I just set up a dimensional analysis with what I'm starting with. I'm starting with 0.64 moles of hydrogen. So automatically you can just kind of by reflex put that down in the bottom right because you know what you have has to go down here. Okay, and what I want is moles of oxygen. I mentioned before, whenever you're in moles, you can freely move from one compound to another within the balanced equation. So I can, because hydrogen and oxygen are both in the same balanced equation, write a new conversion factor of hydrogen, moles of hydrogen, and moles of oxygen. Now I just need to fill in the numbers. Those numbers come directly from the equation. So the coefficient for oxygen is 1, so I put a 1 right there. The coefficient for hydrogen is 2, so I put a 2 right there. Now I've converted from moles of hydrogen to moles of oxygen, which is what the problem asked me to do. This thing right here is my mole ratio. It's just another conversion factor between moles of certain compounds within the same chemical equation, same reaction equation. So now I just do the math. I multiply across the top and divide across the bottom, and I end up with 0.21 moles of oxygen gas. And now it's really important. See, I'm not just writing moles, but I'm writing moles of which particular thing. It's really, really important to be complete and write not just your units, but your units of a particular element. So let's sort of summarize what I did. The first step is write a balanced equation. The second step is write the given. What do you know? What number was given in the problem that's going to help you find your unknown? Identify the unknown. What exactly are you looking to find? The fourth step is to carry out a dimensional analysis that starts with the given and ends with what you're looking for. Pause it here if you need to continue writing. I'm going to move on. Okay, so here's another example. It's a little bit more drawn out with a few more steps to highlight how you would do this. Okay, so you have a reaction written above. It asks you, calculate the number of grams of carbon dioxide that can be absorbed by completing the reaction with a solution that contains 5.0 grams of sodium hydroxide. Okay, so step number 1 was to balance the chemical equation. I see I have 1 sodium here and 2 sodiums over here. Right off the bat, I'm going to put a 2 right in front, and then I'm going to check and see how that kind of affects everything else. You guys have all sort of developed your own methods and best practices for balancing, but that's how I'm going to do it. So I have 2 sodiums now. I have 2 oxygens here plus another 2 oxygens here. That's 4. On this side, I have 3 oxygens plus 1. That's 4. My oxygens are good. I have 2 hydrogens, 2 hydrogens. My hydrogens are good. I have 1 carbon and 1 carbon. All right, I have a balanced equation. The step number 2 we highlighted before was identify your given. I'm given that I have 5 grams of sodium hydroxide. I need to identify my unknown. What am I asked for in this problem? It says calculate the number of grams of carbon dioxide. So that's what I want, grams of carbon dioxide. Another visual cue here just to sort of see how we're going. So we have mass here. We're going from grams of sodium hydroxide. We want to go 2 moles of sodium hydroxide, then use a mole ratio based on the coefficients to moles of carbon dioxide, and then once we've crossed that bridge, we can go down here to mass of carbon dioxide. One more time, follow my arrow. So we're starting at mass of sodium hydroxide. We're going 2 moles. Once we're in moles, we can cross this bridge, the mole ratio bridge, and we are over in moles again, but now we're in moles of carbon dioxide. Once we find moles of carbon dioxide, we can go to mass of carbon dioxide. Now we have the process, we have the roadmap, let's just put in the numbers. So dimensional analysis starting with my given. I have 5.0 grams of sodium hydroxide. I can automatically put that down in the bottom. And what I want, remember, before I can cross that bridge, I need to get into moles of sodium hydroxide. Okay, recognize this conversion as the molar mass. I need to find the molar mass of sodium hydroxide. So inventory my elements. I have sodium, I have oxygen, I have hydrogen. I have, from my balanced equation, from my formula, these don't come from the equation, these come from the formula, of sodium hydroxide, 1 sodium, 1 oxygen, and 1 hydrogen. Now filling in the molar masses of each of these elements, the molar mass of sodium is approximately 23, oxygen approximately 16, and hydrogen approximately 1. If I add that all up, I end up with a molar mass of 40 grams per mole. So 40 goes with grams here, and that's per 1 mole. Okay, so I'm out of grams of sodium hydroxide, I'm into moles. Now I can cross this mole ratio bridge. I have moles of sodium hydroxide. I want moles of carbon dioxide. Now I look to my balance equation. I have a 2 in front of sodium hydroxide, and I have the implied 1 in front of carbon dioxide. I just fill those in. The 2 from sodium hydroxide, the 1 from carbon dioxide. I'm almost done. Now I have moles of carbon dioxide, and I want grams of carbon dioxide. Grams per mole is my conversion to cancel out those moles and get grams. This conversion factor is the molar mass, but now of carbon dioxide. So I have carbon and oxygen. I have 1 carbon and 2 oxygens. Carbon's molar mass is 12. Oxygen's molar mass is 16. If I add those together, I end up with a molar mass of 44 grams per mole. Now I fill that in. The 44 goes with grams, and it's per 1 mole. All right, now I am ready to do the math. I multiply across the top, so 5 times 1 times 1 times 44 divided by 40 divided by 2. And plug all of that in, I get 2.75 grams of carbon dioxide. Okay, now, particulars is grams of carbon dioxide. I'm good, because that's what I was asked for in my problem statement. The only thing really that we've added here is this idea, this new conversion factor, the mole ratio. We can cross the bridge between 2 different mole maps. And it's based on the balanced chemical equation. Okay, if I know I went through this problem pretty quick, it didn't necessarily give you enough time to write it down. So rewind it a little bit, make sure that you have this example problem written down, and be prepared to discuss it in class tomorrow. See ya.